Hello and welcome to Empowered Learning. This video is the second video in the Laplace Transform video series. And so this video will be about deriving Laplace transforms of basic functions that we normally use to do this kind of thing. And so I normally take the time to actually work out a lot of examples in the videos that I normally do for certain topics. For this one, I have already worked out the problems, and I'm doing that really just to kind of cut down on the time on the videos itself. But also in practice, one of the things that we do is we don't say, well, hey, I want to take an ordinary differential equation and I'm going to work out the Laplace transform for every single expression that I have in my equation, and then from that figure out what the Laplace transform is. So in practice, we normally use tables, but I'm going through this exercise because in learning what the Laplace transform is, we normally take the time to practice deriving some of these Laplace transforms for basic functions so that you can get a feel for how this is, okay? But of course, the culmination of this is once we figure out what the Laplace transform is, we're going to compile a table. And of course, that table could be as basic or as extensive as you want it to be, depending upon how many of these types of Laplace transforms you want to derive for however many different types of functions you want, okay? And then, of course, from that, we will use the tables from then on out to be able to do the things that we want to do in solving ordinary differential equations. So saying all that, because I'm just going to step through what I've already worked out, and I'm hoping that this suffices. So our first example will be, how do we take the Laplace transform of this constant function 1 here? And again, we're assuming that this value s is going to be something that is greater than 0, and it is a constant. So using our definition, we literally just let f of t be 1. And of course, 1 times anything is just itself. And then this simply just becomes taking the antiderivative of e raised to the negative st. Since s is a constant, we could use the substitution rule or whatever, but what we end up getting is e raised to the minus st divided by the constant minus s. And we're going to evaluate that from 0 to infinity, okay? But since it's an improper integral, the proper way to actually write that is to take the limit of what you get from the net change theorem from Cal A and evaluate it from 0 to b, where you let b approach infinity. So we're basically going to let b equal t minus, and then let 0 equal t. And that's what you see here and here. We know that 0 times anything is 0 here, and e raised to the 0 is going to be 1. We also know that we have b approaching infinity here, so we're just going to leave this as is in our next step. Notice that both denominators have a minus s in it, so what we're going to do in this case is note that this subtraction and that negative there will end up creating a positive value there. And so we could kind of switch this around. This will look more like 1 plus s like this, and this will be minus e raised to the minus sb over s. And then, of course, we just switch that around to make it look like this. And we pull out the 1 divided by s out of each term. And we see here that this essentially just ends up looking like 1 minus e raised to the minus sb, which is what you end up having here. We let b be infinity. And of course, e raised to the negative infinity goes to 0. So you just have 1 over s times 1 minus 0, and of course all that's just 1, so we just end up with 1 over s. And so that lets us know that the Laplace transform of 1 is just going to be 1 over s. Now we're going to do the same thing, but we're going to do it with our functions t, t squared, t cubed, and t raised to the 4th. And so this is my way of trying to say, well, hey, if we have standard power functions, or put another way, I'm trying to look at what my polynomial terms are going to act like. Well, the terms in a polynomial are going to act like, rather, because we know a polynomial is nothing more than a sum of power functions. And so my goal here is to figure out what the Laplace transform of all 4 of these functions are, so that I can see a pattern that I could come up with for Laplace transform of t raised to the n, okay, where n just basically ends up being a positive integer, or aka a natural number, okay. So for this first one, Laplace transform of t, we just let f of t equal t, and we have this result here. And we see from what we're looking at, we could use integration by parts. So if I was to let t here be the u, and I let all the rest of this be dv, and of course the derivative of t is just 1 dt. The derivative of u would be, in this case, 1 times dt. Since I have dv here, if I took the antiderivative of e raised to the minus st, it's just going to be 1 over s, of course, negative of that, times e raised to the minus t. And I just substitute that into my formula for the integral here by using integration by parts. And we see that once we substitute everything in, of course, this first term here, we're going to have to rewrite that as the limit as b approaches infinity of what all this would be if I let t equals b, and then minus the same thing if I let t equals 0, okay? For this second term here, I just notice that once I do this and combine that to be plus, and I factor out that constant of 1 over s, that this is the same thing that we got earlier, okay? We know that the integral from 0 to infinity of e raised to the minus st dt is just the same as 1 over s, or the Laplace transform of 1, okay? And of course, 1 over s times 1 over s gives us 1 over s squared. And here now we just break out what all this actually means, which is we let b equal t into the first, for the first time, then minus let t equal 0. And so from here, if we keep going, we see that if we deal with this part here, we know that this particular limit, because whatever e raised to the sb is going to be, as b approaches infinity, it's going to grow faster than whatever this is, okay? So in other words, you can look at this as I got a function that's going to be, I'll just put it in terms of x. We have a function y is equal to minus x compared to a function y is equal to e raised to the s times x. And so, of course, e raised to the s times x is always going to grow faster than just minus x. So, of course, this will end up being 0 here. Now, how I did it is I said, well, since this is a constant, I'm just going to ignore that and just carry it to the end. But for here, I can do L'Hopital's rule. And that's basically take the derivative of the top and bottom and then evaluate again. Of course, at this point, you actually do have a constant. You let b be equal to infinity in this case, or more technically saying as it approaches infinity. And of course, the denominator here is going to be infinity, and any constant divided by infinity goes to 0. So we essentially just have 0 plus 1 over s squared, which ends up being 1 over s squared. And that's what the Laplace transform of T is. Just ends up being 1 over S squared here. And so we'll take this and go ahead and move on and figure out what the Laplace transform of T squared would be. So if we do the same thing for Laplace transform of T squared, it's just pretty much more of the same. What's different here is that since we are dealing with T squared instead of T, then we're going to have to do 2 rounds of integration by parts. And so at this point, I employ tabular integration to do it. And since I know that my the function T squared here, if I was to take continuous derivatives of it, it would eventually get down to 0. I can do this form of tabular integration to where I just do successive derivatives of T squared, do successive antiderivatives of e to the minus st, successive antiderivatives of e to the minus st, and then diagonally go across, multiply these 2 terms, minus multiply these 2 terms, plus multiply these 2 terms, and then of course do it over the limits of integration to evaluate what the corresponding integral would be. So in applying the result from our antiderivative, we need to plug in b everywhere we see t, minus, and then do the same thing by plugging in 0 everywhere where we see t. And we see that we've done that here. Of course, for these first 3 terms, all of them are in terms of b. And since we have this limit operator here, we'll just leave those alone for the moment. Whenever we plug in 0 for the first 2 terms, they go to 0. For the third term, we know that this e raised to the st will turn into just 1 because 0 times anything is 0. E raised to 0 is 1. Of course, we have 2 divided by s cubed, and that will be a constant. So, of course, the limit of any constant is just a constant, so we'll keep that in mind. Come to this next row here. For these first 2, since we have b's in the numerator and the denominator, we'll end up having to do, well, we don't have to do it, but I did it here, L'Hopital's rule, to be able to evaluate the limits. For this third term, since we don't have a variable b in the numerator, we can just pull out the constant and look at what is 1 divided by e raised to the b, or put another way, what is e raised to the negative sb, what is the limit of that as b approaches infinity. And of course, we know that any exponential decreasing function goes to 0 as b in this case goes to infinity. And of course, the limit of any constant is just that same constant. Now, after that, we'll apply L'Hopital's rule. For this first term here, we would actually have to apply it twice. Okay, and so the first time we do it, we'll just get 2b, and the second time we would just get b. So that's where we get the 2 here. And of course, that means I would also have to take the derivative of the denominator twice here. And the first time I do it, it'll be s squared e raised to the sb. The next time will be another s being multiplied. So it'll be s cubed e raised to the sb. And of course, any constant divided by some exponential function. Exponential function is always going to grow more than a constant function, so that's why the limit of that goes to 0. For this term, we only have to take the derivative of numerator and denominator once. To do that, same kind of thing, and we see that constant function grows slower than exponential, so limit as b approaches infinity of this is going to be 0 as well. And of course, all that just simplifies to just being 2 divided by s cubed in this case. Okay. And so in seeing that, we see that this is what our Laplace transform will be of t squared. All right, so we need to do the same thing for t cubed and t to the fourth. I'm not going to spend as much time going through all the gory details of it. I just want to kind of show it so that you can see what the results are. So for Laplace transform of t cubed, we know that it's going to be this same integral here. And of course, in working all that, we know that we can do tabular integration again. Set it up kind of the same way. It's just that now we have 4 terms instead of 3 or 2, or in this case 3. And so set it up the same way as we did the one where we were taking the Laplace transform of t squared. Evaluate all terms at b, minus do the same thing at 0. And of course, we kind of see the same pattern here. For whenever we plugged in 0, all terms except for the last one ended up being 0. And of course, we got this 6 divided by s raised to the 4 here, because that minus and that minus multiply to become positive. And of course here, once we actually look at everything, we could basically apply the L'Hopital's rule to each term, depending upon how many times you need. The basic thing here is that all these exponential functions here times these constants are going to grow faster than b cubed, 3b squared, 6b, or the constant function 6. So all those will end up going to 0 at the end of the day. Okay, and so that's what you see here. So all of them are going to 0, and of course all this ends up being 0. We got plus 6 divided by s to the 4th, and we see that that ends up being our final result. Okay, and t cubed, Laplace transform of that is 6 divided by s to the 4th. We do the same thing with t to the 4th, just kind of more of the same. Again, it just gets longer. Okay, so we go through the whole whole process again, and we see that once we do all that, of course it's just longer, we end up with 24 divided by s raised to the 5th. Okay, and so the main thing here is, now that we have a collection of Laplace transforms for 1, t squared, t cubed, t to the 4th, we can come up with a pattern here. And so, of course, what we would notice to start off with is just this. But we notice here that whatever is in the denominator, of course, this is the case when, let's say, n is equal to 0. This is the case when n is equal to 1. Case when n is equal to 2. So we see that the denominator is always s raised to the n plus 1. Okay, so that's where I got this from. So we also see here that if we kind of look at the pattern of the numbers here, we have 1, 1, 2, 6, 24. That follows the pattern for the recursive sequence of what we call factorials, okay? Because we know 0 factorial is defined to be 1, 1 factorial is defined to be 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, okay? And of course, if you've forgotten what a factorial is just, for 4 factorial, it's just 4 times 3 times 2 times 1, okay? And of course, 5 factorial will be 5 times 4 times 3 times 2 times 1. So we see here that all of them would fit this pattern here of, and I think I forgot this here, so this should be a factorial there. So we see that we would have n factorial divided by s raised to the n plus 1. And in general, we could say that Laplace transform of t raised to the n is equal to n factorial divided by s raised to the n plus 1, where n is some non-negative integer. Basically, we could say that goes 1, 2, 3, 4, so on and so forth. Okay. Now, when we normally look at tables of Laplace transforms, we'll see that whenever we have the constant case of Laplace transform of 1, they just state that separately and then state it like this for values of n that are positive. So this would be 1, 2, 3, 4, so on and so forth. So that's normally how you'll see it in a Laplace transform table, and not necessarily like this. All right, so moving on, the next thing that we want to do is take the Laplace transform of some basic exponential functions. And so we're going to deal with the exponential function e raised to the alpha t, where alpha is a real number. And we're also going to deal with e raised to the I alpha t, where, of course, I alpha t would be a imaginary number, okay? So, of course, the Laplace transform of e raised to the alpha t, we just put in place of f of t, e raised to the alpha t. And we notice here, per our exponential rules, basically this exponential rule here, that we can basically add these together. And of course, I've added these and factored out the t. In my next step, I just factored out a negative out of this result here. And this is just some constant. So if I wanted to call this k, then what I literally have is e raised to the minus kt. And if I take the antiderivative of e raised to the minus kt, that's just going to be e raised to the minus kt, all that divided by minus k. And of course, the equivalent of that is what I have here, where k is just s minus alpha. And of course, s and alpha are both constants. So just like we've seen before, once we get this into the form of taking the antiderivative and evaluating the limit of that, and of course we're doing this part because this is an improper integral, we plug in b for everything, minus plug in 0 for everything, and just see what we get. So this is us plugging in b in everywhere where we see t, and then plugging in 0. This result here, for the second term, we end up having plus here, and this is just 1 divided by s minus alpha. So I've listed that first. And then we have minus, goes along with this, and then the e raised to the minus s minus alpha times b, all that over s minus alpha. And so from then we just evaluate those limits again. Of course, 1 divided by s minus alpha is a constant. So limit of a constant is a constant. For here we have our b, and if we let b be infinity here, then of course e raised to the negative infinity goes to 0. So this whole entire limit goes to 0 here. And we see that the Laplace transform of e raised to the alpha t, where alpha is a real number, just ends up being 1 over s minus alpha. Now, if we do the same thing and allow our exponent to be, if we allow it to be an imaginary expression instead of just a real one, we see that the only thing that's different now is that at the end of the day, instead of this being alpha, now it is I times alpha, okay? But everything else pretty much looks the same, okay? And of course, here I've changed the way that this looks slightly, but at the end of the day, it's pretty much the same thing. The one thing that I did differently here is, since I already knew what this was going to look like, I leveraged that in evaluating this to make it a little shorter. So here I changed what the e raised to the minus s minus I alpha, all that times t, looks like, to just make it look like this. And of course, this looks very similar to what I had up here. So I know that the Laplace transform of e raised to the negative zt is going to look very similar to the Laplace transform of 1, where my variable now, instead of it being s, is z. And so that's where I got this from. And then of course I know Z in of itself is just S minus I alpha. So I just replace Z with S minus I alpha, and I have what the Laplace transform of this would be. And so what you're seeing here is a technique that we use as we establish more Laplace transforms for functions. We actually leverage that so that we can make deriving the Laplace transform of other functions a bit easier. So for our next example, we want to do the Laplace transform of sine of omega t. And so I'm doing this just as an example of what it would feel like to take the Laplace transform of either sine or cosine, okay? Cosine would be very similar. Of course, we'll get a different result, but the feel for how we would have to derive it would pretty much be the same. Now, it turns out that we actually have two different ways that we can actually derive the Laplace transform of this function here. And so I go through both ways. So the first way that we're going to do it is the way that we've been doing it before, is by using just basically doing it straight up. And of course, in doing that, I'm going to have to use integration by parts. So in this case, though, we know that neither e raised to the minus st or sine of omega t, neither one of those with its successive derivatives is going to go to 0. So we're going to have to use an augmented form of integration by parts, the tabular way of doing it, to be able to get what we need relatively efficiently, okay? And so if you're not familiar with tabular integration, of course, I basically give you a formula for what that's like here. My comment here is just basically saying I've allowed sine to be my u and my e raised to the minus st, and I probably should put dt here as well, even though you don't have to. I've allowed my u to be the trig function, and I've allowed my dv to be the exponential. We could switch it around and it's still going to work the same way. So that's basically all that I'm trying to say here, okay? So the idea for the augmented integration by parts is we want to take successive derivatives again for the trig function, because we've let that be u, and successive antiderivatives here. And what we want to do is keep on doing successive derivatives and antiderivatives until we see that across from each other we have the basic things that we need to be able to find out what is going to be our integral again. So if we look here, I need something that has e raised to the minus st in it, and I need something that has sine of omega t in it. So here I see I have e raised to the minus st sine of omega t. I know that 1 over s squared and minus omega squared, both of those are constants. So I'm okay with that. And I just keep doing that diagonal thing that I did earlier. But the thing that changes now is once we see that we can recover e raised to the minus st times sine t, we actually go across and multiply these together to let us know when we stop. And that is what you see going on here, okay? So we do that whole process. And of course, once we have everything together here, this is the equation. And remember, even though I have this written down here at the bottom, I could really just rewrite this way. And so here what you see is this term and this term are like terms, so I can put that all on one side. And since this negative omega squared over s squared is a constant, I can add that to both sides, and I end up getting this on the left side of our equation. This ends up being what it is on the right side. And from that point, I just do a bunch of simplification, okay? So if I keep going here, now that I know what the actual antiderivative is, Of course, I got the plus C on there, but since I'm going to be doing an improper definite integral, so to speak, I'm not going to need the plus C. So I go in, I know this is a constant, evaluate the limit of what's left from 0 to b. Do kind of like how we just did before. Plug in b minus plug in 0. See what simplifies, and we'll see at the end of the day, once we do all that, that sine of omega t just ends up being omega over s squared plus omega squared. Okay. And of course, we assume that the omegas here are going to be different than s, and s is really the variable. Omega is going to be a standalone constant. Okay. So this would look something like, if I had, let's say, 5 over s squared plus 25, where 25 is just 5 squared. Okay, so that's what that would look like in an example. Now, example 5 here is just another way for us to establish this particular Laplace transform, and we can do it by using Euler's identity, or Euler's equation. And of course, here we know that if we use this, if we do the right combination of addition, subtraction, and constant multiples of e raised to the omega t, we could form what sine and cosine of omega t would be. And in this case, we see that sine of t is actually equal to this expression here. And so if we were to split it up, of course, factor out the 1 divided by 2i, then we would have this situation here. We already know what the Laplace transform of e raised to the I alpha is. And if we let alpha be omega t, then we know what the Laplace transform of e raised to the I omega t is, as well as e raised to the negative I omega t, same thing. So we come here, take the Laplace transform of this, which means we translate it in integral form. We know that we have the difference of two integrals. Of course, for this first one, in general, we know that the Laplace transform of this is just basically going to be 1 over s minus I alpha. Laplace transform of this will be 1 over s minus negative I alpha, which is 1 plus alpha. Take all that divided by 2i. And then once we do the algebra and simplify all this, what we see is we still end up with the omega over s squared plus omega squared. All right, so for our next example, we are going to take the Laplace transform of a unit step function. And so one of the things that you see here is in how I've defined my unit step function, I've actually defined it in two different ways here. Okay, so you see I've defined it this way as well as this way. The point that I want to make here is, remember when we talked about the Laplace transform not being unique for a particular function. So if you remember back in the first video, that's one of the things that we talked about, was that I could have two functions that will end up having the same Laplace transform if the area under the curve of those two functions is the same. And so this is an example of that. So we see we have our unit step function here defined where basically, and I'll kind of draw it out here, basically where we actually have a defined point at t equals 0. And this version of it actually has an open circle here at t equals 0. And of course, down here, it's all 0, open circle here. And of course, we got an open circle there, all 0. So my point here is that the area under the curve for this and for this is all the same. So if I was to take this and multiply it times e to the minus st, whatever that is, then the area under the curve of that particular function would kind of look something like this. And of course, the area under that curve is going to be the same as it would be for here. Okay, if this was open circle and you did it like that, the area under the curve of both of those functions, if I was to take this and multiply it by e to the minus st as well, would end up being the same thing. And so just saying all that to say that that's one of the reasons why this version of the step function or that version of the step function will still have the same Laplace transform. So it really doesn't matter how we define it. Both are going to give us the same result. Okay. I mentioned this also because you'll have some textbooks define the step function this way, others define it this way. And it really doesn't matter how they define it. As long as the function is starting at t equals 0, whether it's defined or undefined, they're still going to be the same result. Okay. So with that, if we go and look at our solution here, notice that the unit step function was only a non-zero value for values that are 0 and higher. Okay. Now I am going to take the approach of using this version of the step function just so that I can show you that this continuity here does not contribute to what the Laplace transform of the unit step function would be. So if we look at that, we see that, of course, we can just look at the Laplace transform exactly at 0. And then from there, we could look at it again from 0 to infinity. Of course, knowing what we know from first year calculus, the zero width property of integrals, all of this would just be 0. And so that's why we see that here. And then, of course, we know that this particular integral here is the same as just a Laplace transform of 1, which is just 1 over s. Okay. So we see that the unit step function is just going to have the same Laplace transform as the Laplace transform of the constant function 1. And of course, that makes a whole lot of sense because it's essentially the same thing for values of t greater than or equal to 0. Okay. So now what we want to see is what does this look like whenever we take the unit step function and we do a horizontal shift to it. Okay. And when we say horizontal shift, that can be to the left or to the right. So for instance, here, if I said u sub 3 of t, that would just mean the step function with a horizontal shift of 3 units to the right. If I said u sub negative 3, then this would turn to a plus, and that would be the unit step function shifted 3 units to the left. Okay. Either way, we're going to see that pretty much is going to look similar, not the same, but similar to something that we've seen before. So if we take the Laplace transform of unit step function shifted either to the left or to the right, we know that that's going to be replaced by this function here, where we know this could be defined piecewise. Okay. And so we only care about when t is greater than or equal to alpha here. Okay. So if that is the case, then our unit step function, if we look at it from an interval of t from 0 to infinity, then of course, from 0 to alpha would be our first interval. And then of course, from alpha to infinity would be the next. So we're basically saying that, and we're assuming that this is going to be a horizontal shift to the right, because anything that's going to be less than 0 for t really doesn't matter. Okay. But technically we could, shift it to the left or to the right if we wanted to. Okay. So here in this particular situation, we know that for values of t that are less than alpha, our unit step function is going to be 0. And for values of t that are greater than or equal to alpha, we're going to have value of 1 there, okay? Now, we know that 0 times anything is 0. And if we take the antiderivative of 0, that's going to be a constant. And so that's why you see that here. And of course, that constant is going to be evaluated from 0 to b, but it really doesn't matter because we can't plug in the b or the 0 into the constant. When we do the net change theorem thing, we're just going to have c minus c, which still is going to end up being 0. So that's what you see here. Of course, for this situation, this is like saying the Laplace transform of 1 in a sense, but since we have this going from alpha to infinity, we can't just say that it's the Laplace transform of 1. So we actually got to evaluate it. So here we take the antiderivative of e raised to the minus st, know it's this, evaluate it from alpha to b. And of course, if we write everything out, it's going to look like this. Plug in b everywhere where we see t, minus plug in alpha everywhere where we see t. And of course, then from there, if we take the limit of this first term, since our exponential function, if we put it down in the denominator, would basically create something that looks like 1 divided by a constant times e raised to the sb. If b is infinity, then of course all that goes to infinity, and 1 over infinity is 0. And so that's why you see that here. Of course, this 0 came from the fact that the limit of a constant minus a constant is just the same constant as 0. And then of course here, alpha is itself a constant. So the limit of a constant is just a constant. And of course, this subtraction sign here and that negative sign work to be addition. And so we just end up with this constant here, and that ends up being our result. And so we see that the unit step function, if we do a horizontal shift, is going to be just e raised to the negative s times alpha, all that divided by s. And so note here that if we were to allow alpha to be 0, then this would be e raised to the 0, which would just be 1. So we would have the whole case of the Laplace transform of 1 all over again. Okay, so that's kind of how those are connected. So in general here, we see that this is the same result as example 6. And so we can collapse these two identities if we wanted to and just said that, hey, the unit step function, whether it's like this or expressed this way, could just be expressed that way. And we wouldn't necessarily need to know explicitly what the Laplace transform of 1 is if we had the unit step function. We still identify that, but technically speaking, if we were to cite the Laplace transform of a unit step function or unit step function shift, it would automatically include this in it if we gave the conditions that alpha has to be greater than or equal to 0.